All right, guys. Good afternoon. Let's get started. Today's lecture, lecture number 8, is about natural language processing and large language models. So first of all, why is that an important topic? Well, the reason is that, in fact, majority of the data that is available within industry, and especially if we're talking about consumer industry, it's really unstructured data. We do have some structured data. It can be like CRM, sales, Excel, finance. So that type of data that we actually used in some of the models we have considered so far. But at the same time, pretty much all the interaction with customers happens through unstructured data, whether it is customer reviews, customer feedback, whether it is mails, chats, transcripts of the calls, social media, or also like internal communications and internal documents within the company. And so learning and knowing how to work with unstructured media and structured data becomes very important. It is also quite universal. So here we're not focusing on one particular industry. The techniques and the tools we're going to talk about today can be used across multiple industries. Now, so what's natural language processing? Well, it's a branch of AI that focuses on interaction between computers and humans using natural language. And so the main goal for NLP processing is to be able to read language, to understand and make sense of the language and the sentences. So there are a lot of applications. And if you think about this, it's first of all, it is really, human-computer dialogue system. You can think about this as a chatbot or any other, but it is interaction between human and computers. And of course, we would prefer that interaction to happen using human language, not computer language. It is, of course, things like machine perceptions, classification of various natural language, various texts, and what's become extremely interesting recently is natural language generation. And we're going to talk about it. In terms of the use cases, probably, very popular use case, especially for the customer-facing services, is going to be like sentiment analysis or question answering. If we're thinking about all other kind of processing, there's definitely information retrieval and information extraction. So information retrieval means mostly like information search. Extraction is extracting and going from unstructured information in text into the structured information, like in the databases. And for example, machine translation applications. A lot of those applications we're using through, Google services or Yandex services. But there are, of course, models built for the particular verticals. So we're going to look at a few tasks with examples, and then we're going to look at the ways we can solve those tasks. So first of all, sentiment analysis. What is that? Well, it is the algorithms that we use to understand the sentiment of a message, and that's usually can be used for like product reviews or any other correspondence with the customers. So when you can actually looking at the message, understand its sentiment. Here it's very simple sentiment analysis, but you can see that is the sentiment of this message is positive, right? Because somebody is planning to definitely recommend the platform. Another task is so-called NER, or named entity recognition. This is a task of finding within the text entities that are named. So we can actually say that this is their, say, location, right? Or we can say that these are people, right? Here's women, wives, or it's a date, right? Like, for example, 19th century or 1848, or it's a particular person. It's a name, right? Elizabeth Cady Stanton. So the point of being is trying to find out and name different entities within the text. Then another classical problem in natural language processing is so-called dependency parsing, where you could actually try to use language rules to detect dependencies between verbs, nouns, pronouns in a sentence. And that allows you to actually understand, or allows the machine to understand the sentence better, right? So overall, if I think about information extraction task, that the tasks that combines different tools we just discussed. So for example, we take a text, and then we can do annotation on the text, which will be this named entity recognition. So for example, can detect that John is a person, is a name, and location is Liverpool, and Julie is a person. Then we can also do dependency parsing and realize the dependencies. And then we can, in fact, extract information and build, for example, knowledge graph, saying that John Lennon was born in Liverpool, so connection between the name, between the person and location, and also he was a child of, here is Alfred Lennon and Julie Lennon. So this is like typical information extraction task. Overall, there is a standard pipeline that's been used in NLP that allows you to get from some text to through the processing steps. And usually it goes through the tokenizing, which means splitting the text into chunks. And this could be, the level of words or parts of words. Then you can do the tagging of the words, named entity recognition. You can parse text, etc., etc., etc. So there is a quite standard processing pipeline that typically has been used for natural language processing for quite a long time. Now, if we want to go a step further and go from those rules, and that what we just described is really sort of rules applied to text, to machine learning applications, then it is really very, very much classical machine learning application, where we take text, then we extract, we extract features, and then we train an algorithm on some type of, for example, labels, if we want to do, say, certain classification or regression. So, and then we can, for example, say if the review was thumb up or thumb down, by providing examples of positive and negative reviews and sending all the documents, those examples, through this pipeline, through the feature extraction, and then building features and then using sort of traditional machine learning algorithm with the features that we created. Now, the features in the machine learning, in natural language processing, that's probably the most interesting part here, is how to build features. And the standard approach would be through the so-called vector representation and building, term document or document term matrix. And the idea of the vector representation is to represent every document as a vector within the space of and the space is defined by words. So every word is a basis vector, and the document is a collection of this word or a point in this very high dimensional space. So for example, if I have a bunch of sentences like it is a puppy, it's a kitten, it's a cat, that's a dog, it's a matrix, I can collect all the words that being used there, and all these words will form a dictionary. And then each of this, the presence or absence of this word in the sentence will be a feature. And so every sentence can be encoded through a vector. And at first, you can actually have a binary vector, which means the word is present or not present in the sentence. And that's what example is given here. It's a puppy, where it is an a, all of those elements within the vector that corresponds to it is an a are ones, the rest are zeros. But then you can actually go a little bit further and not just use binary vectors, but you can actually put the information in there in terms of the number of words that happens. Like, for example, in the fourth sentence, that is a dog and this is a pen. The is happens to be used twice in the sentence. And so in the vector, you have number 2 here, right? And you can do more the next step would be like term frequency versus document frequency normalization, so you can normalize it, et cetera, et cetera. But the main point of this is that you can actually represent words by vectors. And so, I'm sorry, you can represent sentences as vectors. So here is sort of one sentence, and the sentence can be thought of a point or, a vector in this case as 1, 2, 3, 4, 5, 6, 7-dimensional space. Now, if you think about the dictionary or vocabulary that has been formed by say English language, is going to be like 40-50,000 words. It's a lot. And so that means you will have a vector of that length, and those vectors will be very, very sparse. So you could actually use them to build machine learning, but it's not going to be extremely efficient. It will work, and that's what we have been doing for quite a while. But again, this is a very, very sparse, very large matrix, very sparse matrix. So there are different methods to actually shrink the matrix. You can use principal component analysis, for example, which in the case of language is called latent semantic analysis, LSI. That allows you to make smaller bases, but still the content is almost like one hot encoding, which is, it says, okay, if the word is present, there you go. Now, there is another problem with this representation, is it's really bag of words, in the sense that when we encode information in vectors that way, we completely lose the sequence of words, right? Plus, if we do it, say, sentence by sentence or document by document, of course, there is no connections between documents, right? Now, here it's sentences, but you can think about this as entire documents. So this is a very much sort of the working scheme that has been used in very many algorithms, but it's probably not the most efficient. Now, where can we use it? Well, we can use it for text classification, when we can take a input text, then create those vectors, then send it through classification model, and given examples, we can train the model to predict whatever labels we want, right? And this can be example for either sentiment analysis or just classification of text in different topics, or whatever else you want to do with this. The tasks of summarization can also be quite interesting. Here you actually have a text and you want to summarize it. Like if you have a long book, you want to create a short summary, and the simplest approach will be extractive summarizer that just pulls out a few sentences. Again, this can be done either through some hard-coded rules, like the beginning of the paragraph sentence is important, or with some named sentences are important, or you can train a classifier, or actually you can train a ranking classifier that will rank the important sentences, and then you pull out the important ones. Abstractive summarization is actually harder, where you can try to combine different sentences to create a new sentence, but this is currently done with generative AI very, very easily. So, as we have just discussed, going into vector representation is needed in order to use machine learning methods, because machine learning methods understand numbers and not words. So you need to somehow go from words to numbers, and we do it through this bag of words, for example, approach. And that has been used, that approach has been used for a long, long time. Until, I think it was 2014, right? Until the so-called, skip-grab, the word embedding, skip-gram, or word-to-vec methods appeared. And they literally started this entire revolution in natural language processing. And the idea of those methods is actually quite straightforward. What you would like to do is you would like to encode text and words such a way that for every word, it will be encoded in context, which means we will want to encode the dependency in between the word and its surrounding. How can we formalize this? Well, the idea is that if I give you a word, then the algorithm should be able to predict the words that surrounding this word. So the words that are within some sort of context window. And so, for example, here, if I look at the word, let's say here, the word quick, then the word quick in the sentence, a quick brown fox jumps over the lazy dog, is surrounded by the articles the and by brown here, adjective brown. So what it really means that even if I given the word quick, I should be able to predict the words the and the word brown. So from quick, I can predict the, I can predict brown, and since I have this window, I can predict fox. Then if I take the word brown, and again, this is my window context, I should be able to predict the surrounding. I take the word fox, and I have the surrounding, the context of the surrounding, I should be able to predict this. And so the idea would be that I can actually build a model that for every word predicts other words within the context. And the words can be those that are a little bit ahead of this word or behind of this word in the model. And so I can build this type of classifier, right? So by giving the word brown, it will predict for me the words that goes next to it. And this way, I'll find association in between sequence of words. And I can run this sliding window through pretty much all the text I have. And for every word, find the words that occur frequently within that particular word within the text. And so I can build a model that will predict those words given a particular word. Okay, now you say, okay, well, great, but so what do I do with this? Well, and here is something interesting comes up. In order to build this, one of the ways to build this is we can do it through the neural network and sort of encoding, decoding schema, where you put, again, as an input, we can put our words, and notice that this is the vector representation, this is one-hot encoding. And then I can get the surrounding words as an output, right? Because that's sort of what we're going to be training. We're going to be training on a given word to predict the words that surround it. But what's interesting in this approach, or in one of the possible approaches, I can actually build a neural network with some number of layers. And in fact, I can have a sort of hidden layer in the middle. And then I can use that hidden layer as a vector representation for the word that I put in the input. So it is some sort of space, high dimensional space, but not as high dimension as an input, not like 40,000, but it can be, you know, whatever we decide, units. And within that space, you can have a representation of a word by, you know, this vector. Now, it's not going to be any more zeros or ones vector. It's not a binary vector. It's not a sparse vector. You know, there will be different values in that vector. And so by doing this, you know, putting different words and running through different text, for every word, I will have an embedding of that word, right? Non-zeros, some vector, here it's just 4-dimensional space, for example, but it can be like any other dimension. All right, you would say, fine, you know, instead of having binary zeros and ones, we can, yeah, it is multi-layered perceptron. We're not talking about RNNs here right now. So if you build this, you know, this representation, so what's the big deal, right? So, okay, maybe instead of vector of 40,000 length, you'll have a very short vector. But so what's it? How's it helping us? Well, it's helping us in many ways. Well, first of all, of course, even if you just use those vectors within the machine learning approaches that we discussed so far, it's already going to be much more efficient, compressed representation that we're using. And in fact, this representation encodes information for every word about the surrounding words. But surprisingly, this approach had some absolutely amazing properties, which when scientists have observed, they were very, very surprised. In fact, this type of approach, and the approach I mean representing the word through the surrounding words, in fact, allows for this embedding to preserve semantic relationship. And that is very, very surprising. So the idea is the following, that within this embedding, if you take a word, and let's say, two words, queen and king, those two words will leave, these are vectors, right? And so, there will be, this is a vector for queen, and this is a vector for king. Oops, this is a vector for king, two vectors. What's surprising is that if you have a vector that corresponds to the word woman, and then you apply to this vector the difference between king and queen in terms of the vector. So you take this vector and apply it. Then woman will become man. So somehow we found the representation where semantic relationships can be expressed as linear algebra rules. So when you can actually run and do vector type of operations, and it will do the semantics. So you can actually, instead of queen, king, woman, man, you can say, okay, cities and countries, right? The capital of UK is London. Then you take the vector between London and UK, and then you say the capital of Russia, and add this vector to the word Russia. It will create a new vector, and that vector will point to Moscow, right? And this is very surprising. This is an extremely surprising property, but it has been reproduced in a lot of experiments, and so made people thinking that if we can actually do this, then we can also do a lot of other things, converting literally all the problems that we're dealing with in natural language into the language of linear algebra, right? And use vectors, and then we can add, subtract vectors and do everything we want, but those operations will preserve semantic relations. And here it also shows that it can preserve syntactic relations. And again, the trick, the sort of the secret here is that you represent a word with the help of the surrounding words. And this is called embeddings these days, and the word vec was the first algorithm that proposed that. And in fact, if you do that, and I give you another example. You take a sentence like I saw a cat, and you run through. I showed you one of the examples, but you can have like any other algorithms from the neural network, but that operates on the same concept, that you represent the word through its surrounding, and you build the embeddings. Then what happens that within embedding space, not only you get those very nice properties of preserving the semantics, but also, for example, documents on particular topics will tend to group together in those spaces. And so the embedding happens to be an extremely powerful way to pre-process data, and then you can run the data through any machine learning algorithm you want. All right. So we started with very simple rules to process text. Now we're talking about a very different approach where you can embed text. in some low-dimensional space, and those embedding preserves semantics for the text. And this method actually started this whole revolution that today led us to large language models and generative AI. So before we talk about generative AI, just to remind you that generation of the text is one of the properties of the model, that you can do that if you learn the structure of the text, right? Learn the patterns in the text. And embeddings helps us learn those patterns. So what are those models that are called today like large language models or generative AI? Well, generative AI uses those models to generate text. But what are those models? Well, those are the models those are language models, which are the models that model probability of the sequence of words in language. But they also have certain interesting properties. First of all, they're large, which means they're trained on a very large volume of data, and the models themselves have a lot of parameters. Now, typically, those models are multi-layered neural networks, but they can have a lot of parameters, like the model that run original ChatGPT, which was GPT-3, had like 175 billion parameters, billion 10 to the 9, right? So it's actually very large. The second property of this model is they're pre-trained, which means they have been prepared and trained on the data, and so it comes to you not as just an algorithm, but it comes to you with weights, and it can be pre-trained in a self-supervised fashion, and we're going to talk about it in a second what that means. But the big picture is self-supervision does not require examples from us, so it does not supervise learning. It does need examples, and so those models can be trained on text, images, speech, or any other data. And then when you have this model pre-trained, you can actually, after that, fine-tune it or adapt it to particular tasks or domains. Now, that can be done with examples, with training examples. That part is a supervised learning. So if on the left, we get self-supervision, on the right, we get supervision. And in this case, the interesting part here is that most of the work is done in pre-training phase. That's where most of the computations are done. And when we do fine-tuning, we just adjust model parameters with some examples. And this type of models, they're capable then of doing a lot of things like text summarization, anomaly detection, instruction following, all other things, and it can work in multiple domains if you add data of that type. So again, ChatGPT uses LLMs, large language models. In particular, the GPT-3, that was Da Vinci type of model, and the size of GPT-4 we don't know, but that's again large language model. So how does it work? What's the sort of conceptual story there? Well, the large language model, first, it actually needs to internally understand the language, which is build language model, right? A model of the language. So what's language model? Well, language model is really is a probability distribution of sequence of words. So for any sequence of words that you can think of in this world, we can assign a probability to that sequence. Now, how is it done? Well, you can calculate, for example, if you have a sentence, I saw a cat, you can factor out those probability through the rules of probabilities, the probability of I, then probability of conditional probability of so given I, and so on. But for each of those, you still need to calculate them. So, you have some text and you want to calculate the probability of the next word. So how would you do that? The approach is quite similar to what we just discussed for embeddings. So you can do this in the form of training, and this is what self-supervision is. You don't need human annotators here. Let's say you have a text and you want to predict the next word. So what do? Well, you take the previous words and you hide the next word from the algorithm, and you make it predicted. And then you verify if it's predicted correctly or incorrectly. And then you can actually go and do it for any word. There is another approach, which is, and this approach, actually, this so-called autoregressive modeling, that's what's done in GPT. There is another approach, which is so-called autoencoding, and that's done in BERT. Over here, you actually just hiding, one word, and you try to predict that word through the surrounding words. Notice that that's very, very similar again to the approach that we discussed for embeddings. And then, you take the surrounding, you take this context window, and you slide it, and that's how you train. Now, the key here is you don't again need any human annotation, because all the text is known, and you just masking one word at a time and using surrounding to predict that word. And that's how you train the algorithm. Now, the fundamental difference is that when you train this BERT type of model or autoencoding, you actually need surrounding to predict the word. When you train it in the form of autoregression, it is the previous words that predicts the next word. And that is what you want to have for a language model. And that what allows you to actually generate words, right? Because you're given phrase and you want to continue a phrase, and that what prediction does. So how does it work? Well, you give a few tokens, and that's what is a prompt that you give to, say, ChatGPT. And then the model predicts the next token. Then you give that next token, put it together into the prompt. Now you get a longer sentence, and then the model will predict the next one. How does it do it? Well, because it learned the frequencies and it learned the probabilities. So, what would it look like? Well, the neural network here on this slide is your model. And I'm giving a text, I saw a cat. And remember, I can actually give the encoding vectors, right? Each word is a vector. It can be either, it's very simple one-hot encoding, or maybe some sort of embedding. And then, based on the entire text, and this in the self-supervision, we train a model to predict the probability distribution for any word in the dictionary. And we'll have the vector here, which is shown by this histogram, which is a probability for each word in the dictionary to follow the phrase, I saw a cat. So I saw a cat, and then here is the probabilities. So we can then even sort those probabilities. Now, in order to continue this phrase, you can either select the highest probability, or you can actually sample proportional to the probability. And that's what's usually done. So you have a probability distribution and you sample from it randomly, but that's what will generate the next word, the continuation in the sentence. Now, since it's a process of sampling from the distribution, you in fact can sort of modify the distribution, and you can change relative values, and this can be done through the parameter which is called temperature. And if you go to the site for GPT, to the GPT playground, you can actually have that control parameter, and the temperature allows you to either to change the relative probabilities for different continuation of your sentence. And so when you change the temperature, and again, temperature is sort of just a term here. It changes the distribution, and by that, can generate different continuation for a sentence. But in fact, since it is a random process, anytime you put in some text, you will get different continuation, or quite often can get different continuation. And so you should realize that within this autoregressive model, you generate text word by word, sample by sample. And so, for example, a sentence, a cat jumped onto and then there are different options. For example, it can be little or big. And if your model selects little, then the next sequence of words can be either, say, bed or box. And so you will generate the sentence, the cat jumped onto the little box. Or when you run the same model next time and you give the same prompt, the cat jumped onto, it could actually select potentially, other path. It can say big, big table or big couch. And so that what gives the variety of the results. Each possible continuation is, of course, probabilistic. There are, say, if you have a English dictionary, English vocabulary, then it is, can be like 30 or 40,000 potential continuations, different probabilities. The model samples the words according to those probabilities, and that what generates the text. So that creates the base model. So that is the base model, as what I just described is really this pre-training process. And so it creates this large pre-trained model. Now, the only thing this large pre-trained model is capable of is really predicting the next token. That's the only thing it does, right? It sort of generates the next token. Now, if we want to simply generate text, we're literally done, right? Then we can give a prompt, it will generate text. But if we wanted to be, say, chatbot, to become as a chatbot, to behave as a chatbot, or to, for example, provide us text summarization, then we need to fine tune or train it to do that. Or if you wanted, for example, to speak like on the financial topics, you probably need to add a little bit of financial data. So that part is called fine tuning or adaptation. And that's one of the ways to make the model respond to your comments and to your commands and to your comments. But then there are other ways, and one of them is like, the most standard one is prompt, through prompt, or so it's called prompt engineering these days, which means setting up a specific way of interacting with machine by putting, a sequence of text for the machine to continue. In order to understand this prompt engineering, you just need to remember that the only thing the algorithm does is continues your sequence of words, continues with the most natural for the machine way, which means, if you want to make it do something, you need to provide quite long piece of text in prompt for it to continue it sort of the way you might expect it to be continued. But whenever it does even question answering, it still continues the text you have given to it, right? That's the only thing this algorithm is capable of doing. Now, quite interesting recent development is in creating plugins or chaining, where you can in fact take the model and connect it to outside world through so-called plugins. And you can see that with ChatGPT, when you can connect the model to Wolfram Alpha, which is mathematical engine, or you can connect to the search engine or to anything you want. And so the model is becoming connected. That's what plugins are. Now, prompt engineering allows us to write queries. Fine-tuning allows us to teach the model through the supervised learning to either build summaries of the data or to, for example, perform dialogue by giving the model lots of examples of the dialogues. But again, those are examples. So when we do the fine-tuning, there are a couple of things you can do. You can actually give either domain-specific data, and then again, the model will learn the language of the domain you want you want to use the model in. Or you, for example, can provide labels, and then that will allow the model to acquire new skills. And typically when you do that, you keep most of the coefficient in the model frozen, so you're not changing them, but there are some layers in that network that you update. So prompt engineering by itself also is like almost an art form these days. So depending on the prompt, the algorithm and the ChatGPT will perform differently. So the more detailed prompt you give, the better it works. And for example, here it gives us an example of this so-called in-context learning, where you provide a long prompt with examples, questions and answers, and then the model give it the question and it will answer you. Now, interestingly enough, is that this answer is really the very probable continuation of this text, right? Remember, the only thing model does is generating tokens based on the probability distribution. Now, then there is an example of chain of thought learning. What happens is the models are in fact worked much better if instead of just giving it a task, you split the task into pieces and provide step-by-step instructions in your example. Then the model will try to repeat this and will return to you sequential steps that gives you the result. So it will provide you explanation. Again, it sounds like miracle, but the point is when the model sees the detailedly explained text, the most likely continuation will be the detailed answer. So there are a lot of models like that now out there. As Google calls model garden, model zoo. The first models appeared in 2018, 19, 20. They were quite small by today's metrics. Today model, which is GPT-3, GPT-4, they are very large. We don't know what the size of GPT-4 is, but GPT-3 is 175 billion. And there are models from Google like BART, and then there is a bunch of models that are open source that are much smaller, like Llama, Vicuna. Those models has been open source, and they have a size of like 10 billion parameters. It is still quite large, right? But it is small compared to ChatGPT. And these models also possess a lot of similar properties. Maybe they're not as good as ChatGPT, but they're pretty efficient in terms of what in fact they can accomplish and what they can do. Now, it is also important to understand that those models, they learn from text. And so it is important what kind of text went into the building of the model. And here we see for some of the models it is known. Like, for example, GPT-3 was trained on 84% of web data, right? So Common Crawl, and 16% of books and news. But then there are other models that are quite different. So if we look at the Galactica, it was trained mostly on scientific data. If you look at AlphaCode, it was trained on the code data. If you look at the model called Palm, it's Google's model, right? It is trained a lot on conversational data, but some on web pages, some on books and news, some a little bit on the code. And so this mix really gives the model, that's from it is actually from this mix where the model learns the probabilities of the words in the sequence, and depending on that data, it interpolates, right? Extrapolates. So predicting the next and the next and the next token. So that's why it's critical to understand sort of what the models has been trained on in order to understand its properties. And so there are many more models out there, and there are some models that, probably worth paying attention to, like GPT, like this new sort of GPT-3 plus or GPT-4. There's a Palm from Google. There are other startups providing models like Anthropic and Cohere, and they're like open source models. All of that are, available right now for experimentation. So here are a couple examples going back from this technical part to business part, how it can be used and how those models can be used like sort of out of the box. We're not talking about building a very special model for a particular business, but this is like literally you take ChatGPT, what can you do? Well, one example, you can actually take, say, customer review and ask the model to summarize it. How do you do this? Well, you literally put the prompt, summarize your review, in some number of words, and it will do it. Or you can actually be more focused and say, like, summarize this review with particular focus on the price and value. And so it will be able to put this together. Or shipping and delivery. It will actually extract that information. Now, this is quite amazing because previously, in order to do this, we would have to train the model by giving you those type of examples. And remember, we started the lecture, you have to go through this entire pipeline and train the model to do this type of summarizations with some sort of supervised learning. Now we don't do this. You have a pre-trained model, you just literally take it out of the box, you give it this review, and you just have to put together a good prompt. Or, we want to do marketing product description. There you go. You can actually give an instruction to the model, which is write a product description based on the information provided in the specs, and give those specs. And then you can ask, like, format in particular type, and let's say format is HTML, and you can actually ask to include a table, and you give that specification through a file, and the model will create for you the entire description for the product. So you can imagine what effect they will have on the workforce. Literally, a lot of people who are currently employed in creating those type of description, in writing reviews, can be replaced by this type of models. And they can and they will. And this also follows for a lot of legal documents, technical documents, marketing copy. And I'm sure you have heard about the models like DALL-E, or in Russia there is a model from Sberbank Kandinsky that generates images. So, but from the text description, so those models will be able to, by giving the text description, will generate images. So again, sort of building marketing material. So there are a lot of professions now that will be significantly changed with these tools. And remember, it's all started with very simple natural language processing. In fact, the field of natural language processing, remained quite boring for like probably 10, 15 years. And the most interesting things that were happening in the field were the search engine and maybe the translation, the statistical translation that Google created. But there was no other advances until several years ago with the introduction of embedding, and then now with those large language models, they have been in development for the last 5 years, and now we see these amazing results. So they can be applied across very many fields and very many domains. But in order to understand in depth how they work, right, and overall the field, as always, there are several books I would recommend. There is a classical book on natural language processing with Python on LTK. And then there are very, very strong textbooks by foundational statistical natural language processing and speech and language processing. These are like sort of classical books. If you're interested in the topic, that's where to look for the answers. And with that, we're done for today. Any questions?
Yes, one question. Will the lectures published? Will be they are published?
Yes, I do put, there's a recording and I do put PDF files. They're available. I think we're putting them regularly in the chat in our Telegram channel.
Okay, thank you.
All right, guys. And if you haven't tried, either the Bearbank version or Yandex version or, ChatGPT itself, I strongly recommend you trying it because it's quite an interesting and sometimes, astonishing experience. All right, with that, thank you very much. Bye.
Thank you.